Hey there guys, happy Monday. Sorry for the wait on this latest video. I was unfortunately sick last week, but everything is good now and we're ready to get back to business and try a problem that covers a new topic. The description of this problem has two parts, and the first part is really just giving us some context about a way that we could store energy using rotation. The idea is to spin an iron flywheel that's 10 centimeters thick, and we'll simplify things by modeling its shape as a disc. Now, in case you're wondering what a flywheel is, here's a picture of one that was found in an abandoned power station located in the United Kingdom. It's that massive wheel-shaped thing among all the machinery there. The second part of the problem description tells us how much energy needs to go into this flywheel and how fast it needs to rotate. And it's up to us to figure out what the diameter would have to be in order to satisfy those conditions. Additionally, we need to get the centripetal acceleration of a point that's located on the rim while this flywheel is spinning at the 90 revolutions per minute rate. There's not enough information here to use rotational kinematics or really any other familiar strategy. So we'll need to talk about an entirely new quantity, one that is referred to as the moment of inertia. If you're already familiar with what that is, feel free to skip ahead. Otherwise, let's explore this a little. But first things first, we should take a minute to reflect on what is meant here by the word moment. The language can feel a little misleading, but whatever you do, don't confuse it with a span of time. The everyday definition of the word moment and the physics definition are totally different. Just like when it comes to the word theory. In the context of physics, a moment is defined as a distance to some point, which is then raised to a non-negative power and multiplied by some physical quantity. So that's what's meant by the word moment here. It's pointing specifically to this general definition. The moment of inertia takes this concept and applies it to objects experiencing rotation. In that situation, the physical quantity is mass, and the exponent n will equal 2. Let's take a look at a few examples. Here's a single particle with mass m rotating about some point at a perpendicular distance from the rotational axis r. The moment of inertia of this solitary particle is simply mr squared. But what if we had a bunch of particles instead? Maybe something like this. Well, thankfully, nothing really changes. It doesn't even matter if they all have different masses and radii. Their individual moments of inertia are still mr squared. And if we want the moment of inertia of the entire system, well, then we just add them all up. It's that easy. What isn't easy is finding the moment of inertia of a large continuous object, because we would have to use a calculus approach instead. We'll worry more about the calculus stuff later, but in the meantime, here's a really helpful table of different results that you would get for the moments of inertia for some common geometrical shapes. Now, I haven't really mentioned what the moment of inertia is, what it represents. I've only shown the different ways that it can be defined, depending on the situation. In simplest terms, the moment of inertia is just a measure of how hard it is to change the rotation of an object. If your moment of inertia value is small, well, then it's really easy to make adjustments to the rotational motion of an object, and vice versa if the value is really large. We saw in the last problem that when an object is spinning, we have to change our kinematic formulas to use new quantities that involve rotation. Things like angular displacement and angular velocity and so on. There's actually another variable that we have to switch out as well, and that one is mass. So the moment of inertia can also be thought of as playing the role of the mass variable for objects undergoing rotation. And that is about all we need to know in order to take care of this problem. Let's go ahead and get it started. The problem description gave us density, and that's a pretty big hint that we should use the relationship between density, volume, and mass to solve for m here, which we can then switch out with the moment of inertia later on. Let's multiply both sides by the volume, which can then be replaced by the formula for the volume of a cylinder, which is pi r squared h. I know that h typically refers to the height, but in this situation, the height of the disk and its thickness, they're the same thing. So we're going to say h is the thickness, and that's that 10 centimeters value that we were given. And we'll have to convert that to meters later on. So now we have an expression for the mass of the disk in terms of known variables, except for r. To get around that, let's try out a new rotational equation. We know that the energy of movement is associated with kinetic energy, but in this situation, the movement is entirely rotational. So let's take 1/2 mv squared and switch out the linear variables of mass and velocity for rotational ones. And here's what that looks like. With that complete, the expression is going to be equal to that 10 megajoules of energy that we want the disk to hold on to. We need to find a way to relate this moment of inertia to the mass expression that we just had on the last slide, the one that incorporates the volume of the disk. How are we supposed to do that? Well, you would need to look up the moment of inertia for the disk. And we can get that from the table that I showed earlier. It's 1/2 mr squared. We're going to plug that expression in for I, and now we can substitute the expression for mass from before. And I'll plug that in next. There are a lot of parentheses here, and the great thing is they're not really all that necessary, since everything is just being multiplied together. So let's do ourselves a favor and save on some writing by expressing the left-hand side like this. Remember that we ultimately want to solve for a diameter, which means solving for the radius would be super helpful. Let's go ahead and multiply both sides by 4 to get that fraction on the left out of the way first. Next, we should divide both sides by rho, pi, h, and omega squared, which will leave the radius to the 4th power on the left-hand side. To get the radius by itself, we'll just raise both sides to the 1/4 power. And with that, we can start plugging in our numbers. Notice in the denominator here, in fact, right in this section, we're making a switch from revolutions per minute to ultimately radians per second for omega. It's very important that you don't forget that part. Otherwise, you'll get the wrong answer. When we multiply all of this together, and then we take it all to the 1/4 power, we arrive at a disk radius of approximately 3.68 meters. And from here, we can just multiply the radius by 2 to get the diameter, which is 7.36 meters. And now we have our answer to part A. In part B, we need to find the centripetal acceleration all the way at the edge of the disk. We can actually grab a familiar equation from previous chapters that'll help us out here. This one. Now, we don't know what the linear velocity v is, but we do know the angular velocity. Recall that the linear velocity v is equal to r times omega. So we'll go ahead and insert that in for v and then square the numerator. The r in the denominator will cancel with 1r in the numerator, and so we'll end up with the centripetal acceleration being equal to r omega squared. And we know both of those quantities. So let's go ahead, plug them in, and finish this problem up. When I punch all of this into my calculator, I get the following result. Approximately 327 meters per second squared. And that is our answer for part B. And we are now done. Thanks for watching, everyone. Have a great day.